last day of the workshop on multi-agent RL and Bandit learning. So to start us off today, we're really excited to have Ioannis Panageas from UC Irvine joining us. And he's going to be telling us about his work on convergence of multi-agent policy gradient in Markov Games. So I'll let Ioannis take it away.
Thank you for the introduction. I wish I was there, but due to teaching duties, I have to give this talk remotely. So this is a joint work with Stefanos Leonardos, who is a postdoc of Georgios, and he's going to join King's College. Will Overman, who was my student, and he will join Stanford as a PhD, and of course Georgios. So we are going to talk about policy gradient methods and in Markov Potential Games, and we are going to talk about positive results along these lines. So what are multi-agent systems? So there is no need for introduction. You can think of it as decentralized systems where you have like a lot of individuals. These individuals might cooperate or compete with each other. There is rationality, and of course you need to use optimization in some distributed way. And there are many like applications like self-driving cars, auctions, robotics, and so on and so forth. So what is the goal? The goal is typically to make predictions about the evolution of such systems. Okay. So yeah, the introduction is very brief because by now, of course, there have been many talks on the area. So let me go through the formal framework. So in the multi-agent settings, effectively, multi-agent reinforcement learning, the framework is very similar to the single agent case. So you have n agents, okay, you have a finite state space. Now you have a joint action space, which is like the Cartesian product of the action space of each agent, okay. You have also a transition probability model. So given the actions of all the players, of all the agents and the state they are, there is a probability to transition to some other state, S prime, okay? Each agent is associated with a reward function that depends on the state and the joint action of all players, okay? Which is a finite number, let's say between 0 and 1. And for infinite horizon Markov processes, we use a discounted factor, gamma. If it is finite horizon, we may assume that gamma is equals 1. And we care about a solution concept that we call Nash policy or Nash equilibrium. This is debatable. There might be other solution concepts like coarse correlated equilibria, but please note that there is no notion of optimality as opposed to the single agent, because now every agent has his own value, his own reward. So every agent wants to maximize his own value function. So sometimes you can imagine that it's impossible that everybody can maximize simultaneously their values. So we care about the Nash policies. So what is a Nash policy? Effectively, you can think of it as a tuple of policies, so that if you freeze n-1 agents, effectively the remaining agent plays best response. So plays his optimal, plays a policy that gives him the optimal value if you have frozen the rest of the agents, and this is true for all the agents, okay? So that's the definition of a Nash policy, and this is like the same notion effectively as a Nash equilibrium in normal form games, and more importantly, Nash policies always exist. This is something that is really important, otherwise this notion wouldn't make a lot of sense, you know, if there was no universality of the notion. And yeah, if you freeze all the agents but one, effectively you define a single agent MDP. Okay, so you can think of it as every agent plays best response if you fix the rest of the agents. So this is the solution concept we are going to examine today. Let me start by giving an example of a two-agent zero-sum Markov game. So you have like two states, the state S0 and S1, and you can think like that the transition model says with probability P, you jump from state 0 to state 1, and with probability Q, you jump from state 1 to state 0. At state 0, the two agents play rock, paper, scissors, and at state 1, they play like matching pennies. So this is what we call a two-player stochastic zero-sum game. So these settings are more or less well understood by this time. Effectively, Shapley showed that these two-player zero-sum games, stochastic two-player zero-sum games, have always a value. In particular, you can show the min-max theorem. So min-max equals max-min. Note that this does not carry over from von Neumann because you don't have convexity and concavity on the value functions. So this is a huge challenge when you have RL settings. You don't have a normal form game, so your value function is not linear or convex with respect to your variables for each player. Okay, so this was like one of the let's say main ingredients that was used in the Scala-Xental to show that if you run like two time scale policy gradient, effectively you can recover Nash policy in two-player zero-sum games. Okay, and I would like to note that in general, finding a Nash policy in multi-agent settings is hard. It's computationally hard, and this is trivial from the results we know in complexity theory for computing Nash equilibria. All the negative results carry over to the multi-agent settings. Okay. I would like to note that you know, more recently there were like a couple of papers that showed even for weaker notions of equilibrium concept, even in like coarse correlated, even in this case, computing a coarse correlated equilibrium under like some assumptions, stationarity and Markovian policies, it is hard. So in general, the problem is computationally hard. Nevertheless, there are like methods like policy gradient that is commonly used and is very successful. So what is policy gradient? Effectively, you can think that policy gradient is like gradient descent, gradient ascent on the value function. Okay, so effectively, if you run gradient ascent on the value function and you do some sort of projection in the simplex, you have a candidate algorithm that might perform well. And by well, I mean, of course, it will not run in polynomial time in the description of the process, but hopefully it will run. It will give an answer in a good amount of time. And typically, how we parameterize the value function? Well, we use like the direct, what we call the direct parameterization, where effectively every number is associated to a variable. So by every number, I mean every policy for every player, you know, the probability to play some particular action given the state, this is associated to one variable. So effectively you have like points in the simplex, and this is how you parameterize your value function, and then you run policy gradient on these values, on the value function. So for single agent cases, there was the paper by Agraval from 2020, and they showed that, you know, if you run policy gradient, after 1 over epsilon square iteration, you reach an epsilon optimal policy. So this is true for single agent cases. And this was effectively generalized in under some other assumptions, like you have 2 times scale, etc. Was generalized for two-player zero-sum games. So in the Skalakis et al. Paper. I mean, when I first came across these two papers, the question that arose to me was, could this policy gradient works for single agent and 2-0 sum stochastic games? Does it work for more general settings? Okay, so can we have any guarantees for more than 2 players? That was the question that I wanted to address. And this is what I'm going to address in this talk. Basically, I want to define like classes of stochastic games where effectively policy gradient ascent gives guarantees about convergence to our solution concept, which is the Nash policies. So this is going to be the talk, the talk for today. The notion of the class of games that I'm going to define are called like Markov Potential Games. So Markov Potential Games effectively is a notion that is the generalization of potential games that we have in classic game theory. So what is a Markov potential game? Where effectively it's a Markov decision process with multi-agent settings, so many agents. And you assume that there exists an energy function called potential. Okay, this is like a state-dependent function. So that if any of the players, so say that every player uses some policy pi I, if one player deviates from his policy, the difference in this energy function is captured by the difference in his value function. So, and this is true for all possible agents and all possible deviations. So this is like exactly if the game was stateless, this is exactly what the potential function, the potential game is in normal form games. Well, this notion is kind of important in classic game theory because it captures routing games. It's a class of games that we know that they always have pure Nash. They consider easier than two-player general sum games and so on and so forth. And what is cool about this class is that we can also show that deterministic Nash policies always exist. By deterministic, I mean that if an agent is at a particular state, it plays an action with probability 1. Yes?
Quick question. Is your action space here continuous? As in like or
no,
like
it's a finite action space.
And are the previous results also for a finite action space?
Yes. What I have mentioned right now is for the two papers are for finite action space.
Okay. And would this definition hold for compact like continuous action spaces, or would you need to modify this, you think?
Yeah, I mean, you can, that's a good question. So for actions, yeah, I mean, it goes over, but only the action space can be continuous. Okay. So yeah, the definition can carry over. Sure.
Okay. Awesome. Cool.
I'm not sure if the results carry over. It's not clear to me, but the definition, yeah. So
okay. Cool.
yeah.
Cool. Thanks.
Sure. So what is cool about this notion is that deterministic Nash policies always exist, and by deterministic I mean that at particular state you play an action with probability 1, so it's not a distribution over actions; it's just a deterministic choice. And what is kind of surprising, and I'll show you examples in a moment, is that when you have this Markov potential games, if I just give you, the graph and the transition model, it's not clear whether it is an MPG or not. So characterizing MPGs is not an easy task. Of course, if I give you the function phi, or if I give you the values of the players, then you can check whether or not it is a potential game. But if I just give you the transition model, it's not easy to come up with to understand if it is a potential game or not. So let's see some examples of potential games. So here is an example of an MPG. So this MPG here is a two-player game. You have 6 states. Okay. So in the first state S0, people play matching pennies, okay? Depending on the choice. So if both players play heads, you jump to state this one. If players play tails, they jump here. If one plays head and the other plays tails, you jump here. And if the first player plays tails and the second head, you jump here. And then deterministically, you go to state S1, in which in state S1 with probability P0, you go back to S0. And with probability 1 minus P0, you remain at S1. In S1, you play a potential game. So this is a two-player potential game. So in these four states here, what you do is effectively you play, it's like a dummy game. So you have only one strategy and you are guaranteed to get these payoffs, these rewards. So it turns out that this particular game is an MPG. So there is a function phi that captures the deviation of the players. But note that what is kind of cool is that at state S0, the game is a zero-sum game. So all I want to say from this example is that you might have states where the associated game to that state is a zero-sum game, but overall, the whole RL process is an MPG. So yeah, you can have sub-games that are zero-sum, okay? So this setting, the Markov Potential Games effectively seem to capture cases like that. Here is another example of a game that is not an MPG, probably, but we call it an almost MPG or an ordinal MPG. So how it works, you have like, again, two players, two states. If you are at state 0, if both players play +1, they remain at state 0. If they play anything else, they jump to state 1. So at state 0, these are like the values. This is the payoff matrix. And at state 1, they both get value 0. Okay. It turns out that there is no value function that captures the deviations, but this is an ordinal MPG. So what is an ordinal MPG? Let's go back to the definition. So here the equality is violated, but what it matters is that the left-hand side has the same value as has the same sign as the right-hand side. So in particular, if the left-hand side is positive, then the right-hand side is positive. If the left-hand side is negative, then the right-hand side is negative. If such a case works without equality, then we call it an ordinal MPG. And the results we are going to see in a moment, under some weak assumptions, they carry over for ordinal MPGs as well. Unfortunately, what is also true is that if you have like a setting where every sub-game is a potential game, this does not guarantee that the whole MDP is a Markov potential game. And here is an easy example. Again, two players, two states. At state 0, the first player gets always a 2. The second player gets always a 0. This is reversed at state 1. And the transitions happen like this. So player A and player B, they choose something. If the XOR is 0, you remain at state 0. If the XOR is 1, you jump to S1. And the same is there. If the XOR is 0, you remain at state 1. Otherwise, you jump to state 0. So this, you know, every state effectively is a dummy game, right? So it's a constant game. You always get 2 and the other player gets 0 or the opposite. So they are trivially potential games with a function, with a constant function as a potential. Nevertheless, this process simulates effectively matching pennies. So what is the takeaway message from this game is that transitions can create competition. Most importantly, you can show that this is not a potential game, and you can show that there are no deterministic Nash policies. So yeah, it's not about the sub-game, it's sub-game, it's also about the transitions. If the transitions depend on the choice of the actions of the players, then you can have anything you can imagine. Okay, so this is the takeaway message from this slide. So what is our main results? Effectively, our main results are the following. Suppose that the players, they run policy gradient independently, meaning that I just see my value function and I update according to my value function, okay? And this is true for every player. What it can be shown is that after 1/epsilon² iterations, you can reach an epsilon as policy, okay, for Markov Potential Games. What I want to say is that this 1/epsilon² has a dependence on, depends linearly also on the state space, and it depends linearly on the sum of the action, of the cardinalities of the actions of spaces of the agents. So one might say, okay, since this is like you have an underlying function, what you can do is you can define a one agent game, define a meta player that effectively has as a value function the potential and try to solve the single agent case. Well, this is true, and it will give you also in 1/epsilon² running time, but the dependence on the action space is different. So you have a Cartesian product for the joint action space. Nevertheless, in our setting, we assume that every player effectively updates independently. So the running time depends linearly on the sum of the cardinalities of the action spaces and not at the product, okay? And this is kind of crucial because, one of the main obstacles in multi-agent RL is the huge action space. And this result is under the assumption that we have full information about the value function. This might not be realistic, so we also have finite samples, okay? So we can show the same result if the agents update independently using stochastic policy gradient method. And the rates change a bit from 1/epsilon². It's 1/epsilon⁶. Same dependence on the state and action space, okay? Nevertheless, I'll talk about it a bit later, but you cannot use the direct parameterization due to some difficulties. You need to change your parameterization. And last but not least, I want to say that the deterministic result effectively matches the single agent case. So let me talk a bit about the proof for the deterministic case and also for the stochastic. The first observation that is true also for normal form games is that if you take the partial derivative of the energy function, the potential function, with respect to some variable, let's say that is associated to player I, this is equal to if you take the partial derivative of that player's value function with respect to the same variable. So effectively, all I'm saying is that the gradient of phi is effectively the concatenation of the gradients of the value functions. So what this enables us to do, effectively, we can run policy gradient on phi. Even if we don't know phi, we know its existence only. As long as we know vi, we can run policy gradient or effectively its gradient ascent on function phi, okay? And this is true because of this key lemma. So we don't know phi, but we know vi's, so we can run policy gradient on vi's, but this coincides with gradient ascent on phi. The second key lemma that is also very important is that you need to connect the stationary points of phi, the first order stationary points of phi, with the Nash policies. Again, our goal is to find Nash policies, to converge to Nash policies. So when you run first order methods, you are guaranteed to converge to first order stationarity. So somehow we need to relate the two. So it turns out that the stationary points for phi are exactly Nash policies, okay? So this was true in Agraval et al. Paper and Daskalakis, Foster and Golovich paper. They use this technical lemma that is this property, this very nice property that is called gradient domination. So gradient domination property is like a weaker notion of PL condition, okay? Which, what does it say? Effectively, if you have a function f, okay, and you see f at optimality minus the value of the function f at some arbitrary point x, this difference is of the order of g of x, where g is some notion of first order stationarity. So in particular, you can think that the right-hand side is the norm of the gradient. If the right-hand side is the norm of the gradient, stationarity implies optimality, okay? Because if the gradient is 0, it means that at x naught, let's say, it means that f of x naught is equal to f of x star. So gradient domination effectively says that stationarity implies optimality, okay? And this is true here for Nash policies. So stationarity for multi-agent implies Nash policies. And of course, we don't compute exactly the Nash policies, so we approximate. So the key lemma 2 better carry over for approximations as well. So it is true that approximate stationary points for phi are also approximate Nash policies. Okay. So without further ado, then we use a very standard result that if you run gradient ascent or gradient descent, I have in this slide, you are guaranteed to converge to stationarity after 1 over epsilon square steps, as long as your function is smooth, so it has ellipsis gradient. And this is trivially true because of this descent lemma. You can show that if you have a function f that is smooth, then if you run a step of gradient descent, your value always decreases. Okay, so if you do that like for t iterates, and you assume that you haven't reached stationarity, you can reach some sort of contradiction. So effectively, if your function is smooth, is lower bounded, then after 1 over epsilon square steps, you are guaranteed to reach an epsilon stationary point. And by epsilon stationary, I mean that the norm of the gradient is at most epsilon. Okay, so this is very, very well known and by now a folklore result. So combining this with the previous 2 key lemmas, it trivially follows the result for the deterministic case. Okay, well, trivial is not the correct term because you need to show also the smoothness of phi. Okay, so you need to show that phi is Lipschitz gradient, but we don't know phi, so we need to work with VIs. So you need to show that the gradient of VI is Lipschitz, okay? And we can show that where the Lipschitz constant depends on the number of agents, the number of actions, and the discounting factor gamma, okay? So also I'm going to talk about the stochastic case. For the stochastic case, you need something that is called an unbiased estimator of the gradient, and also you need that the gradient is the estimator has also bounded variance. So it turns out that the estimator that was provided by Daskalakis, Foster, and Golovitz in their paper effectively is an unbiased estimator. So what is this estimator? Basically, at every iterate, okay, what you do is you take an epoch. Well, what you assume that gamma is the probability now that your process terminates. So, and what you do is at every state you take a sample trajectory under the interpretation that gamma is the probability, basically the probability to keep going, and 1 minus gamma the probability to terminate the process. And you take this estimator where this term is just the sum of the rewards of the sample trajectory, okay? And it turns out that the expectation of this term gives you exactly the gradient for the value functions. So it turns out that this is what we call an unbiased estimator. But this does not guarantee convergence for stochastic settings. And the reason is this: imagine if that you have a lot of noise in your estimator. Effectively, you can think that you can go anywhere. So unbiased estimator doesn't give much. You need also that the variance of this estimator is bounded. Nevertheless, also in the Daskalakis et al. Paper, they showed that the variance is unbounded. Okay. Now, if the variance is unbounded, what you can do is basically change your parameterization. As long as you change your parameterization and with appropriate choice of the parameters, you can show that the variance becomes bounded. So what is the parameterization we use? So what is called alpha greedy parameterization, basically the interpretation of alpha greedy is this: with high probability, I play the policy I have, and with some small probability, I play uniform distribution over actions. So effectively, the greedy parameterization has also an exploration term here, okay? And having this exploration term here, effectively what it does, it pushes you away from the boundary. And the boundary of the simplex is what makes the variance of the estimator unbounded. So effectively, under this parameterization, you can have like bounded variance of this estimator. Nevertheless, since you have this exploration term, it means that you will not find an exact Nash policy, right? So this is an extra error you need to accumulate when you do the approximation. So basically, it turns out that if you choose the greedy parameterization to be the square of the step size of your process, you are guaranteed to give an epsilon approximate Nash policy. So yeah, after 1 over epsilon to the 6 iterations, you are guaranteed to converge to a Nash policy. And the difference between 1 over epsilon square of the deterministic and 1 over epsilon to the 6 of the stochastic is due to this exploration term we have here in the greedy parameterization to avoid the unboundedness of the variance. So these positive results are about Nash policies in Markov Potential Games. So we have stronger notions, okay, but we have like, so Nash policy is a very strong notion, but we can do it only for restricted settings like Markov Potential Games. It turns out that 6 months ago, there were like 2-3 papers that almost concurrent, same month, that they talked about effectively general sum games, but the solution concept they care about is not Nash policy, is coarse correlated or correlated equilibria. Okay. So there is a paper also by Zhang et al. That they have almost identical result to ours. The stochastic case was subsequent work, but in their case, they don't use the same estimator as we do. They use a more, I would say, natural estimator that they also guaranteed to show that is unbiased and the results carry over, so they match the running time. Also, there is a paper by Song et al. That they propose an algorithm that is not like the agents do not update independently, so you allow only one agent to update at a time. Okay, so think that in our case, all the agents update simultaneously. Okay, if you assume that one agent updates at a time, they have a 1 over epsilon cube convergence guaranteed for the stochastic case, which is like a big improvement of the 1 over epsilon to the 6 we have, but it's more centralized. Okay, and even more recently, like a couple of months ago, there is this paper by Ding et al. well, they focus also on Markov potential games, and they effectively circumvent the gradient domination property. They do some improved analysis. So they have improved rates, and also they do function approximation for the setting of Markov potential games. So this is one of the first results about function approximation for multi-agent settings, though the result is only for linear functions. And yeah, I mean, technically, I guess it will be more challenging if we have non-linearities. So these are like some interesting works. And let me talk a bit about future directions for the remaining 3 minutes. So right now, what I talked about is policy gradient and convergence to Nash policies for Markov potential games. Nevertheless, I didn't talk about the properties of the Nash policies. In particular, we know that in Markov potential games, you always have deterministic Nash policies. Okay. Is there a way to show that if you, let's say, start at random from some policy, you are guaranteed to actually converge to deterministic policies, or you are guaranteed to converge with high probability or with probability 1, you know, under maybe using these techniques from dynamical systems and so on and so forth. So yeah, can we talk about deterministic Nash policies? One other thing that I want to talk about, and I think this is a really, really interesting future work, is the following. Right now, instead, people do not actually use only policy gradient methods. They use something else that's called natural policy gradient. So in natural policy gradient, what is really happening is that you avoid a term that is called the mismatch coefficient in the running time. And this is true for single agent settings, okay? Moreover, natural policy gradient is a method that is really important because you have something that is called softmax parameterization, and effectively natural policy gradient is used also to do neural policy gradient, which is a way to prove a function, to do function approximation. So understanding the rate of convergence of natural policy gradient for multi-agent settings is really a cool, it's really a cool future direction. Right now, what we know is this, along with Fox, McClear, and Overman, we showed that in potential games, Markov potential game, natural policy gradient converges, has last iterate convergence to Nash policies. So in the limit, you reach a Nash policy, but we couldn't prove rates, okay? So Zhang, they have a paper that they prove rates, but they have some very strong assumptions. And these assumptions make the setting very restrictive. Even more recently, like 2 weeks ago or even less, there is a paper that talks about natural policy gradient, but you have entropy regularization. In these settings, for normal form games, they guarantee to show rates of convergence. And yeah, for me, it would be really interesting to show rates of convergence for natural policy gradient for multi-agent settings, avoiding this mismatch coefficient, okay? Yeah, this is a very interesting future direction. But even I guess more conceptually interesting is to go beyond competition or cooperation. Right now, most of the results we have seen for Nash policies, at least, they talk about either zero-sum games or potential games. Also, I want you to note that trivially, if you have full cooperation, this is a Markov potential game with, so if everybody gets the same reward, then the potential is just the value of all the players. So Markov potential games trivially capture full cooperation. So what happens in settings where you have like both competition and cooperation? In particular, imagine settings where you have two teams that they compete with each other, okay? Effectively, what is happening is that players inside one team, they cooperate with each other, okay? But on the other hand, players of opposite teams, they compete with each other. So this type of settings, they seem to be easier than general sum games, but nevertheless are harder than zero sum and potential games. So yeah, we have some partial results along these lines, but this is also a very interesting future direction, especially because of all the negative results, computationally hardness results that have been shown recently. One question would be, what can we prove? Okay, what positive results can we prove? And yeah, with this, I guess I'm done. Thank you so much.
All right, thanks a lot. Let's see, do we have any questions in the audience here? Oh yeah, I didn't.
Hi. So looking back at Shapley's and Monder's papers on potential games, they propose an algorithm that converges in finite time, which kind of like sounds like coordinate ascent on the potential function of the game. So I was wondering if you could obtain a stronger result here, that you would converge actually to Nash equilibrium in finite time in this setting, maybe considering something like coordinate ascent, which kind of sounds a lot like the algorithm that actually Shapley considers in that paper. Like, it feels like there should be a stronger result that holds here in potential games that we don't get here right now.
Right. So I think the best we can hope for is 1 over epsilon. So this is like the rate that you can achieve when you run for single agent. Okay. And I feel that you probably are right. So I forgot to mention one future direction also is to have some accelerated method. I'm not sure if you use coordinate descent, you can get better than 1 over epsilon square. My feeling is that it might be the same, but
I guess I'm not concerned by like the speed of convergence as much as like the actual convergence solution, because like Shapley converges to an exact Nash equilibrium.
I see. You can, right. So yeah, I'll tell you. So if it is, so you are talking about exact. So that's your problem, right?
Yeah,
so,
yeah, exactly.
So you in polynomial time, and by polynomial time I mean like in the description of the game, you cannot guarantee convergence. So fast convergence. So if you want to talk only about convergence, then the easiest thing you can do, okay, is take all possible. So I told you that deterministic policies always exist, right? So if you don't care about the rates of convergence, what you can do is just enumerate all possible pure deterministic policies, and you are guaranteed that one of them will be a Nash policy, and you can find it exactly. I think what is really important is to do it fast and also do it in a decentralized way. So that's the point of these methods. If you really want to talk only about exactness, the easiest way is to just enumerate all possible deterministic policies and find the one that is a Nash policy.
But that doesn't sound like how Shapley gets finite time convergence in his paper. Like, he doesn't enumerate all the actions. He just has a series of like improvements constantly. That seems like brute forcing it.
Yeah, but he's not guaranteed to converge fast. He will not converge fast. That's what I'm saying.
Okay,
I see. A lot of time. So finite time doesn't mean like fast, right? It might be exponential in the description of the game. And this is there are results, that can show you that effectively you need exponential time unconditionally in some cases. So yeah, so you can, of course, yeah, you can do that, but you are not guaranteed to have a decentralized way, and you are not guaranteed to do it in a fast way. So this algorithm here guarantees that, if epsilon is 0.01, you can do it after 10,000 iterations.
Cool. And I have another question, which is just like a preliminary question. You said that the min-max theorem is not guaranteed to hold in zero-sum games because in general the value function is not convex concave. But
Sure.
if you thought that the sequence of the sum of the scan of convex concave function is convex concave once again, but the reason that we need like the proof of existence of optimum policy in zero-sum games is because we want to prove that it's independent of initial state distributions. The reason why I'm asking that is because you haven't have you told us if your value function is guaranteed to be, I guess maybe you don't need convexity here. Okay.
So the value function, no. So the value function is not convex. That's what I'm saying. But for zero-sum stochastic games, Shapley showed that the game has a value. Okay. So effectively, this means that the min-max, so whoever plays first, I'll tell you it in another way. So say it's a stochastic two-player game. So it doesn't matter who plays first. Okay. You can always guarantee to have an equilibrium solution. This is what it means. Nevertheless, it's not convex or concave. Yeah. But there is a value function. Sorry, a value of the game.
Limit of like convex functions convex again.
Wait, I need wait.
So okay, never mind. Okay, thank you. Thank you.
Thank you.
I think so. Yeah, definitely. Here.
So I have one close-ended question and one more open-ended question. A very nice talk, by the way. The close-ended question is, would a lot of this potentially extend to settings which can be written as a potential game, Markov potential game, modulo a monotonic transformation? So let's say you had a function on the values and that function is monotone, and you can still get potential structure. Do you think there's scope for extending it? Do you think it's easy to extend everything here to that?
So not everything. So if you, for example, the monotonicity that you are mentioned, if you can guarantee that there is a constant, okay, CI, let's say, so that the difference between the energy, the potential in the deviation is equal to some constant CI times the difference in the value function, then everything carries over.
Yep.
The problem is that monotonicity itself does not guarantee that the results carry over, because you might have a vanishing term that is associated with, let's say, the difference of the values. So it might be the case that the difference in the potential is huge, but the difference in the values is really, really tiny, or the other way around. So as long as when the difference in the value functions is not too small or too large compared to the value to the difference of the potential values, then yeah, the results carry over. So only with monotonicity, no, the results do not carry over. I mean, the results.
Yeah, that makes sense. You need some kind of bounded slope.
The rates of convergence do not carry over. Yeah, the rates of convergence. Yeah.
Yeah, that makes a lot of sense. And my more open-ended question was, do you think, or have you thought about easy like recipes for verifying that a Markov game is a Markov potential game? I'm curious about how you came up with those examples.
So right, that's a great question. So if you know the value function is easy, okay, you just take the partial derivatives and you check equality. Say that you only know the transition model and you don't know anything about the phi or v or the v's. There is a way to characterize MPGs, but in terms of computationally, right? If there is a fast way to do it or not, the answer is no, I think. So. And the reason is, I'll give you an easy answer. So even in normal form games, right? So if I give you a setting and I don't tell you anything about, basically, I cannot tell you anything about the game. Like only you can query about the values. It's not easy to learn if the game is a potential game or not. So I have a feeling that characterizing, so there is a characterization by Shapley in particular, but this characterization is not something that you can do it fast. Okay.
Right. This
So-
is in terms of the derivatives, like you were mentioning, I think.
Yes. The easiest way I can answer this is that if you have the value functions, take the partial derivatives, basically, and check if you have equality. I think this is the easiest way. But if you have no clue about the values, it's kind of tricky.
Got it. Yeah, that's a nice answer. Thank you.
Sure.
I guess maybe I had one last question. You kind of briefly mentioned this at the end. So like, in the Agarwal et al. Paper for the single agent case, they have this like distribution mismatch coefficient, which is looking at kind of like the ratio between like the density for the optimal policy and the initial state distribution.
Correct.
And then, in the paper with like Kostas and Noah, we kind of had like like a 2-player analog of this quantity.
Correct.
I guess I was wondering what the kind of multiplayer analog of this looks like in your paper.
So I'll give you an easy answer. Take like the ratio between any policy over the initial distribution.
Yeah.
And take the maximum of all these. This is a bound on the mismatch coefficient. So in your paper, you take the max over let's say over all policies, but you take the mean over the policy of the other agent, right? So you had this kind of definition. So in our case, think that you take the maximum over all joint policies. This is your numerator in the visitation probability. Okay, find the maximum over all policies and then divide it by the initial distribution. So you need full support, first of all. You need full support. So you need your initial distribution to be of full support.
For sure.
Yeah, so it's the maximum overall joint policies.
Okay. No, I guess I was wondering, like, if there's any hope for getting something tighter than that in this setting, or if you think it's like, kind of fundamentally more challenging.
Yeah, you can restrict it only to Nash I mean, instead of the maximum over all joint policies, you might take the max from all the Nash policies. So restrict the set to all the Nash policies, okay, and take like the maximum visitation probability from all of them, and this you can define the mismatch like this.
I see. Okay, interesting.
It's huge. It's huge. It can be exponential in the
sure
in the effective horizon. Okay, that's why I mentioned that it's really important to remove this mismatch coefficient.
Yeah, for sure. I agree.
And the natural policy gradient does that in single agent settings. Okay. Yeah. So, but for your paper and the multi-agent settings, we have this obstacle, the mismatch.
Cool. All right. Yeah, I guess we can chat more about that offline. But thanks a lot. So why don't we thank Ioannis again? Cool. So we'll have a quick break now, and then we'll be back at 10:15 for Drew Food and Works talk.
See you guys.